Let us see what is the watt hour requirement for the battery. The watt hour load is watt hour night by the efficiency. So you see that in a normal condition, the day load, watt hour day, is supplied by the photovoltaic panel, and the night load is supplied by the battery. The photovoltaic panel will charge up the battery to accommodate the night load, and when the insolation is not present, the battery will see to it that it supplies sufficient amount of energy for the load. This efficiency factor here is included to take care of charge discharge losses. So this watt hour night by efficiency will take care of the night load plus the battery charge discharge losses that we have already discussed. Now this is if the PV panel participates in supplying to the load every day. However, just now we discussed on number of days of autonomy. There can be cloudy days, there can be contiguous days without significant amount of sun power. Now let us say that NA, number of days of autonomous operation, number of days of autonomy, is not zero, which means you could have one day without the PV panels participating. There could be 2 days without the PV panels not participating, and so on. So if we take this NA not equal to 0, then what is the load that the battery has to supply? Of course, it has to cater to the night load of that day, which is watt hour night by efficiency of the battery, plus it should take care of watt hour day plus watt hour night, which means the entire load of the day by efficiency. Now this would be the entire load of the day, and the battery has to supply this complete load for the entire day for how many hour days the sun power is not available, which is the number of days of autonomy into NA. Now this would give you the total watt hours that the battery has to cater to. So this can be simplified as watt hour night by efficiency of the battery to NA plus 1 plus watt hour day by efficiency into NA. Now select the battery chemistry. Example, let us say a lead acid battery, tubular lead acid battery, which has deep discharge characteristic of about 80% DOD. So normally one would choose this for a PV application. Tubular lead acid battery, deep discharge of 80% DOD can cater to continuous long-term loads, and the ampere hour of the battery can be calculated as watt hour load. This watt hour load is as calculated here, which includes the efficiency of the battery also, divided by DOD into V battery nominal. For the example that we had discussed earlier, recall that it had three loads: load 1, load 2, load 3. Load 1 was a continuous 48 watt day-night load, a 24 volt DC. Load 2 was a water pump, 3 times daily, 1 hour duration, again 24 volt DC. And load 3 was 3 amp at 24 volts every 2 hours for 6-minute duration. And we had the day load of 612 watt hours and the night load of 914.4 watt hours. Let us use this value for selecting the battery, calculating the battery capacity. So V battery nominal is 24 volts, DOD 0.8, which is 80% depth of discharge. NA is equal to NR, that is number of days of autonomy, number of days of recharge. We will set it to 0 because we are designing it such that the photovoltaic panels are participating in supplying to the load every day. Watt hour load is watt hour night load by efficiency of the battery, which is equal to 914.4 watt hours by 0.7. I'm taking 70% efficiency for the battery, which is a practical value. Watt hour efficiency of the battery is 70%. That's a practical value. This turns out to be 1306 watt hours. The ampere of the battery can be calculated as 1306 watt hours by 0.8 depth of discharge into 24 volts as the battery nominal voltage, and this comes out to be 68 ampere hours. And we have seen earlier that the load current maximum is around 6 amps under non-overlap conditions, and the load current average is around 2.65 amps. If you consider 68 ampere hours and 6 amp, you see that, let us say we take a 70 ampere hour battery, and if you choose a C10 rate, so it will be around 7 amps. 70 ampere hour divided by 10, 7 amps charging and discharge rate, and therefore we could go in for a battery which is 70 ampere hours C10 or C by 10. This is a worst case design in the sense that you are seeing to it that even the maximum current rating is within the C10 rating. The capacity is preserved, but this will result in a bigger size battery and costlier battery. However, we could also go a bit more conservative in the cost by choosing the 68 ampere hours and the average current 2.65 amps. This will result in selection of a battery of 70 ampere hours and C20. C20 will give approximately 3.5 amps, which is still much greater than 2.65 amp average, and therefore even this will work better, but at maximum current discharge, the maximum current discharge 6 amps will be more than the C20 value, and therefore there can be slight loss in capacity. But if that is permissible, then it may be advantageous to go for this because it is definitely